and I am not going to say more about the exposure classes, but please pay attention to the changes, and this is the main and the most important. Well, we have introduced in this chapter this new concept of exposure-resistant classes that was mentioned by Hans, and is durability classes. We discussed on the name, and finally is exposure-resistant classes. And this conceptually is substituting the previous methodology in what was called the structural classes. The manner you select the cover is that you go to the exposure classes. After you had to select a structural class for reinforce or for pre-stressing, and after with that you have the cover depth, and also with the cover depth and the exposure classes you have the mixed proportion in EN 206. Well, now all these of the structural classes disappear, and it appears the new concept on exposure-resistant classes. The cover depths are these in this moment, one for carbonation and another for chlorides, and they are organized by exposure classes, and in this vertical part you have the exposure-resistant classes. Exposure is the X, and the R is the difference between the exposure-resistant class, that is the type of concrete, is different from exposure class that is not has this R. And they were classified in 8. It can be more or less than these ones, and also in 10 for the chlorides. And the cover depths are suggested for this. And the calibration of this cover depth is what has been made by modeling. Stainless steel is the same. We have first the types of steel, the stainless steel that are considered here, because there is not only one type of stainless steel, there are different alloys, and you have the tables for the different types, and there is this table in the Annex Q that you have the exposure-resistant classes that you can apply with the corresponding cover depths. Also pay attention is cover depth for durability. We have also the cover depth for bond and other type of cover depths later on. Well, how to fulfill or how to comply with this new concept? There will be the mixed proportioning and of course the crack width and so, but for the type of concrete, is the EN 206, and the exposure classes, you have the mixed proportioning. And this is summarized in Annex P now. And this will be allowed during some transitory period, not yet defined. And we are preparing a future, because it has not yet been completely agreed, that is called EN 206 part 100. Why 100? In order to differentiate from part 1 and part 2, that are the most common ones. We select 100 because it's a round value, it's nothing more than that. And there is being defined the exposure-resistant classes for carbonation, seawater, and de-icing salts. And you can comply with either, again, by concrete composition, not yet decided, but that will very much nationally decided, because the cements are different in each country, but there will be some general rules in the EN 206 part 100, or by testing. And testing is very important for the new green cements, because they are unknown. They are unknown, the performance in the future. And this is one of the main difficulties to fully agree on the exposure resistant classes, how to categorize them, how to separate the class 0.5 from the class 1 and from the class 2. Which numbers? Again, will be nationally decided, but at least we need to give some general guidance. I will say only, please read very carefully the definition. Each word has a meaning and is very important. And them, because all of them are key aspects for the definition. The most I am going to emphasize is that the classes for carbonation will be defined by the carbonation rate, and the classes for chlorides by the coefficient, the chloride coefficient, diffusion coefficient. In that case, the numbers in the carbonation rate or the chloride diffusion coefficient will be those classified here, and that we still don't agree on the values, because the problem is that, in particular for the chloride, well, one of the problems, there are several, is that the coefficient, the diffusion coefficient decreases with time. In that case, it depends on the type of cement that decreasing. In that case, to extrapolate from the short-term test, that is what is going to be defined there, to the long term, because the performance is at 50 years or 100 years, that is the difficulty and the diverse opinions of the different countries. But in any case, the definition is made on reference conditions, because the reference conditions are those of the testing, of the test method. And also there will be a probability of failure. I mean, there will be, like in the strength, a probability of failure that is with around 7%, a beta value of 1.5. Well, we have the Annex P, simply to show that there is the Annex P that is trying to summarize what was in the previous one, that is for structural class 0.4, the water cement ratio, the strength, the amount of cement, and this for S4. And well, also I was a member of the working group 3 dealing with assessment of existing structures. You will find a complete paper by members of INTEMAC in the issue, in the Hormigón y Acero issue, but only to say that is mainly limited to non-deteriorated structures, and there are only few comments on deteriorated structures. I think that this is a gap that for the future Eurocode has to be improved, because we have more and more deteriorated structures. And I think that this is mine. No, this is you. Well, we have also a new limit state that is called condition limit state, but you can call it also corrosion limit state or durability limit state, depending on the type of attack, on the type of process. But as a general framework, we call condition limit state. And that means that we will consider a part of the propagation period within the service life. And this is one important difficulty for agreeing on the exposure-resistant classes, because in Spain, we learned from the HyA 08 that we have an annex there, and we have the models and the possibility to have this limit state based on cracking. In that case, in Spain, we are familiar with this annex of our code to deal with the propagation period, but this is not the rest of the countries. In that case, when we try to define the exposure-resistant classes, we constantly insist that we have a propagation period, because for carbonation is very important. Some of the green concretes will depassivate very quickly, but after the corrosion rate will be very low, and in that case they can fulfill the 50 years with no problem, but it's necessary to consider a propagation period. And to just interiorize that is complicated for most of the delegates of the country.
Okay, I'd like to just bring some notes about the cover calibration we used for the 1992, the new revision. As Carmen said, we have been moved to the new exposure-resistant classes to define the concrete performance with, against the aggressives. But still there are some improvement on some clauses relating other attacks, like the abrasion or ecclesiastic reaction or so on, that improves a little bit the text in the durability topic. So The degradation mechanism we better know is the corrosion of reinforcement. That's the reason we spend a lot of time just discussing these models and try to calibrate the cover, which I try to summarize here. This information is in the paper, and this is the model we presented in the task group, and it's one of the models selected for the table you will have. So as Carmen said, we got the service life period, which is a sum of the initiation period, the time of the aggressive reach the river, and the propagation period, which is the period in which the river is active, the river corrosion is active. So we have considered a time life schedule of 50 years and 100 years, and we have considered propagation time required to achieve either 50 microns or 500 microns. These microns are taking into account the onset of cracking. So the limit state we consider is just an appearance of visible cracking in the cover. Not much cracking, but just a cracking caused by the reinforcement corrosion. So for the modeling, we have used on the left side, you have the modeling we have used for carbonation ingress, which is the CV model with the square root. And on the right side, you got the chloride ingress model, which is a typical diffusion coefficient with aging factor or variable factor here in the coefficient of diffusion. So what we did for the beginning is just a calibration procedure, which is knowing which is the actual safety factor for serviceability condition of onset of corrosion, which is the calculation of actual beta C. Beta is closely related to the failure probability of corrosion. So we calibrated both the DAN 1045, which is the German code, and the EHA 08, the Spanish code. You will see in the top the carbonation state, which is an average position of 2, which is cheaper to design versus carbonation than versus chloride, where you will see that the average value is about 1 on the bottom and 0.8 in the left side. One of the points I want to stress is that using SIM1 concrete, which is still that was still allowed by the EN 1982, the reliability value are negative, so that represents that the failure probability is 100 than 50%. So we're expecting failure with this type of concrete. So
2 minutes.
Jose Maria says about the alpha. The alpha is giving you the sensitivity of the problem of durability depending on the corrosion onset. For carbonation, we have the cover, which is the C, the carbon ingress ratio, which is the VOC, the wetness period, which is the time of corrosion is active, and also the corrosion rate. But for the chloride sake, as the corrosion rate is so high, you may see that the corrosion rate has no influence in the allowed propagation period of 500 microns. Only the cover, the velocity of the chloride, and the aging factor. The aging factor is a key exponent in the equation. What we did from the beginning is try to uncouple the propagation period from the beginning. Then, as we got from this previous analysis, we got the alpha values for the corrosion rate here and here. We use these values to propose some kind of propagation period in design, taking into account the beta values and the alpha values you got there here. And then at the end, you got which is the remaining initiation period we're allowed to. You may see that, for instance, for quite dry environment, which is AC1, AC3, the propagation period is a bit, maybe half of the time of 50 years. So these are the models you got in the paper. You may read about that. They were calibrated. One of the most interesting figures is the figure on the right. The figure on the right is a comparison of the four models used in the calibration procedure. There are one model from Switzerland, one model from Spain, one model from France, and one model from Denmark. I think you may see that all models are more or less fitting all together. So unless the continuous discussion, the proposed model, which are mostly the model you got in the paper, are fitting the final values. And the last figures I show you, with present recommendations, the use of SIM1 for those more aggressive chloride ingress, I said XA2, XD2, and XC3 and XD3 is above the probability of failure is high above of recommendable. So with the current proposal, durable colors cannot be achieved using SIM1 cement in this type of environments.
You have to finish, please.
Yes, the last one, last points. All the tables are provided as national demand parameters because some countries think their weather or the climate or the environment condition are a bit different. So there are all of them provided as proposals, but all of them are not national determined parameters. They are calibrated for 50, 100 years, including this global corrosion. Quite important, the carbonation are calibrated for humidity ratio of 75%, which is typical from Central Europe, but not for Mediterranean Europe. The tables for Mediterranean Europe may differ a bit, and the difference you will see in the background document and also in the paper. And we adjust some deviation for the next fractals. And we also take into account some additional allowance for different contraction tolerances that may be modified by national determined parameters. So that's a summary of everything. If you got any doubt, you got the paper with all the models and all the data.